So students, today we're going to look at another example of how to solve a structure using NMR spectroscopy, using particularly a proton NMR. And what I'm going to show you today is an example where we have a multiplet resonance and try to tell you how the multiplet arises and how to use it in structural elucidation. So this is the example that I've chosen for you, and you can see that this example has 4 proton resonances, and if we look carefully at these resonances, you see that most of these are in the shielded region of the spectrum. These two are very shielded, and these two resonances are slightly deshielded, but not as far downfield as 3.5 to about 4.5, where we see proton groups which are directly bonded to electronegative atoms like oxygen or nitrogen or chlorine or fluorine, but these are atoms which are bonded probably to an electronegative group like a carbonyl group. I'm going to start analyzing the spectrum, and initially we see a resonance in the methyl region of the peak, methyl region of the spectrum, and the fact that it is a triplet indicates that it must be next to a CH2 group, and if the CH2 group was only next to the CH3 group and not next to any other protonated group, remember that there's still one other group that goes onto this carbon atom. If it were only to that carbon, the CH2 group was only bonded to the CH3 group and not to any other protonated group, we would end up with this CH2 group being a quartet. And if I look at my spectrum, there isn't a quartet in my spectrum. This is a multiplet, which means that there are many lines in this resonance that you see here. So the CH2 also cannot be a triplet because it is already a quartet, and if there was something else here, that quartet would get split into something bigger, so it can't be split into something smaller. So this CH2 group isn't this triplet that you see slightly deshielded. So in all likelihood, this CH2 group is this multiplet here, which means that there's another protonated group going to be attached to the CH2. If I look at my other 2 resonances, because we've taken care of that and we've taken care of that, right? So this must be the multiplet, that must be the CH3, and if I see which other protonated group, it's either that one or that one. It can't be this protonated group because this is a singlet that's not next to any other group. So this must be next to some group that has no protons on it. So then it would have to be, the group that's bonded to the CH2 would have to be this particular resonance, which integrates to 2, so must be a CH2. And we have this CH2 now appearing as a triplet because it's next to the CH2 group here and not next to another protonated group. I count up my carbons, hydrogens, and oxygens. I don't have any oxygen in my structure, so I need an oxygen in my structure. I have 1, 2, 3, 4 carbons, but my molecular formula tells me I should have 5. I have 3, 4, 5, 6, 7, 8, 9, 10 hydrogens, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. So I have all the atoms that I need to solve the structure. In putting them together, I need to make sure that the valency makes sense, and to do that I make 4 bonds to carbon, and I end up with this ketone, CH3, CO, CH2, CH2, CH3. If I look at this structure again and then try to make sense of the spectrum, this should be a triplet in the methyl region. It is. This should be a multiplet because it's next to the CH2 group and the methyl group. So there are many protons here, right? Two different kinds of protons, 3 and 2. So this should be the multiplet. This should be a triplet next to a CH2 group and not next to another protonated group. So this next to the CH2 group makes it a triplet. It's slightly d-shielded because of the carbonyl group, and that's what you find here. The CH3 group is a singlet because it's not next to a protonated group, and it's slightly d-shielded because of the carbonyl group. Thank you for watching, and I've got one further one for you after this.